It's very important as exam point of view. Let A is equal to 1, 2, 3, 4, 5. Define a relation R on A cross A by, look at the relation x1, y1 is related to x2, y2. If and only if the condition is both are equal, both elements, addition of these two elements x1, y1 is equal to x2, y2. And you have to verify whether this relation, this kind of generally defined relation, is an equivalence relation on A star A. Determine the equivalence class 1, 3, 2, 4 and 1, 1. Determine the partitions of A cross A. Now you should not get confused how to write this equivalence class for this kind of elements. We had done in the previous case for a single element 1, 2, 3. Why? Because in that relation R was defined on the set A. Okay, but here the relation what they have defined is defined for A cross A. So A cross A is your Cartesian product. So every element of this is already a ordered pair. Okay. For that they are writing the relation. Right. So with this we go for explanation of this particular example. So I'll start with first sub question. Since it is very general, we start with the general statement itself. For the first property, I have to take reflexive property, right? So I will just take xy belongs to A cross A. So as per the definition here, if any two elements are related under R, then they have to be, since there is if and only if, they have to be both equal. Okay. So as per that, I can write x plus y again, which is equal to x plus y itself. Because we know that this is a trivial statement. X plus y is whatever the value of x and y, x plus y is equal to itself. Okay. So I can write the statement by trivial definition. Therefore, from this, I can convert into this form. So xy is related to xy itself. Okay. Because as per this, if this is the case, I can write like this. If this satisfies, I can write in this way. Since there is if and only if, both in both the ways, the statement is true. So with that, we are writing this. So are we able to find out it is a reflexive property? With single element, you are writing like this, right? A is related to A. For every element, A related to A is called reflexive property. Here, instead of A, you have an element of the form ordered pair because you are doing this for A cross A set. Okay, that's why XY I have to take. XY is related to XY itself, therefore it is true for all the elements. So for all XY of this kind, this is, you're going to get this relation. Therefore, it is a reflexive property. Next. Once this is done, I have to move on to symmetric property. From the first itself, symmetric property, we have to check. To check the symmetric property, I should take two elements, right? So one element of the form x comma y, then r comma s, or else we will take like this x comma y. In terms of x1, y1 we will take, and x2 and y2. We will take two elements of this kind in the set A cross A. But for the symmetric property, I have to check an element of the kind x1, y1 if it is present in R relation. Okay, if x1 y1 is related to x2 y2 in R, then I have to find for this element is related to the first element. Okay, so we will try that. From this, as per the definition, you can write like this. From the definition, x1 plus y1 is equal to x2 plus y2. From the definition, we have written like this. Now, we have to just simplify this, reorder this to obtain our required results. What is that reorder I am doing here is, I will take this term to the left side. Swap left hand side to right hand side, that's all. x1 plus y1. Okay. Now, if I look at this, any element which are equivalent, which are equal, I should be able to write in this template. Therefore, x2 comma y2 is related to x1 comma y1 as per the given condition, given definition. Yes, we started with this and we proved that the second element is related to first element. It's of the kind what? If A is related to B, in the symmetric property, you have to prove B is related to A. That is what we are proving here. In place of A, you have x1, y1. In place of B, you have x2, y2. I hope you understood this statement and explanation. Therefore, it is satisfying the symmetric property also. Moving on to next, transitive property. For proving transitive property, again we have to start with three elements. So I will just take x1, y1, x2, y2, x3, y3 belongs to A cross A. It is in the set A cross A. Then I have to look into the element which is present in the relation. So I will take x1, y1 in general, assume that x1, y1 is related to x2, y2 and x2, y2 related to x3, y3. So both are there in the relation. Then what is my job? My task is to find out this element is related to this element, right? As per the transitive property. So for this, as per the definition, we will write the step first. x1 plus y1 is equal to x2 plus y2. Similarly, we write for this also. x2 plus y2 is equal to x3 plus y3. Okay. Now this is equation 1 and equation 2. Combine equation 1 and 2 and simplify that. This is having some value. I will substitute that. So it becomes x1 plus y1 is equal to x3 plus y3 by combining these two. So what is going to happen when I combine these two? So anything which is equal, two elements are equal, then you will be able to write in this form as per the given definition. Therefore, x1 plus y1, x1 comma y1, this element is related to this element, or x3 plus, x3 comma y3. Yes, we are able to prove that with this condition, we are able to prove that the first element is related to the last element. Transitive property is satisfied in general. Okay. Therefore, we verified that R is an equivalence relation. Yes, R is equivalence relation. Any doubt here? Next, moving on to the second one, you have to determine the partition induced by R. So how do we prove this? We will start with the first element. We have to find out equivalence class of 1, 3. So as per the definition of the equivalence class, how do I write equivalence class of any element? Set of all x, but here it's not x because your element is not in a single value, it's an ordered pair value. Therefore, ordered pair value in general xy such that, or it is taken from A cross A, any element from the given set, such that if that element is related to this element, then it comes under its class as per the definition of equivalence class. So we write like this as per the definition. Now we expand this as it is. Okay. Here, anything which is written of this form can be replaced with this value as per the definition. X plus y is equal to 1 plus 3, right? Now, x plus 3, sorry, y is equal to 4. So what is the meaning of this? If any two elements are added, if that sum is 4, then you can say that that element is related to this set. So you can just try to find all possible combinations which will result sum as 4. So what are those combinations? Because your A is 1, 2, 3, 4, 5. What are all other possibilities? 1, 3 itself, same element, which will also give you 4. Yes. Similarly, 2, 2 will also give you 2 plus 2, 4 as per the definition. Similarly, 3, 1 will also give you 4. Only these three elements comes under this. Therefore, all these elements are related to 1, 3 and they comes under equivalence class of 1, 3. In the similar way, you can also find out for other, that is 2, 4. 2, 4 equivalence class. As per the definition, we know that a sum is 6. So what possible combinations of values will give us a 6? We can write it here as a elements. What are all other possibilities? 3, 3, right? 2, 4 itself. Okay, 2, 4 which is already taken. The same element can be taken. 4, 2 also, right? Any other combinations to give 6? Yes, 5, 1 and 1, 5, right? No other possibilities? Yes, that's all. Similarly, we will find out for 1, 1 also. 1, 1 is result should be 2, right? As per our previous explanation. Therefore, any other combinations, no other combinations, it is none other than the same element. Therefore, 1, 1. So these are the values for the second sub question. Any doubt here? Moving on to the third category, partition of A cross A induced by R. So how do we find out this? We start with all in elements, equivalence classes, find out all this. Similarly, 1, 3 is already done in the previous case. Similarly, 2, 4 was also done in the previous case. In the similar way, other combinations can be tried. 1, 2 or 2, 1. Whatever you do, you get same collections. Similarly, 1, 4 combination is not tried. You can try this. You have to try yourself all these combinations. Then 2, 5. Then 3, 5. 4, 5. 5, 5 at last. 5, 5. Because each one is distinct here. So this will give you 10, sum, 9, 8, 7, 5, 2, here 6, 4, 2. Okay. So according to the sum value, you can try to find out other combinations. Now, by combining which value of this will give you partitions is very much important. Because if I take 2, 4 and 4, 2 will result the same value. So since the partition says that intersection of any two blocks or sets should not be, should not have any value. It should be null value always. Therefore, are distinct. Therefore, you have to select here which are all the distinct elements which will give unique value. Say 5, 3 will give you 5, 5 will give you result 10. We will select 5, 5. Among 4, 5 and 5, 4, both will give you same 9 value, or we will select only one, 4 comma 5. Okay, any one. Here 8 you will get, here 7 you will get, 5, 3, 6, 4, 1. So by combining all these, you can say that it's a partition defined on A cross A. All these elements together. So P can be defined as all these equivalence classes, 1 comma 1, then union 1 comma 2, and so on. All this, the last element is 5 comma 5. So this is how you have to simplify all these kind of sub questions. Any doubt here? If you don't get involved in the class, you are the losers. Remember that. If you come later and ask for the doubts, definitely I will not entertain those things. In your regular class, you have to be very alert and listen for the class. Get your doubts cleared in class itself. Okay, so no doubts. You want to try other problems? Do you want to try? No. Okay. Since we are having all these portions for the internals, let me complete other few things today itself, because only one class I am getting, right. Tomorrow no class for me. So I am moving on to this material is already there in the Google Drive link which I have shared. You can go through that. Moving on to next topic, that is called partial order. A relation R on A is said to be partial ordering relation or a partial order on A. The condition must be satisfied, that is, R has to be reflexive, R is antisymmetric, R is transitive. Look at this. There is a correction or change in the second property. If R becomes symmetric, we say it is equivalence class, okay, equivalence relation. But here partial order is the second property is not symmetric, it is antisymmetric property. That's all. You know that how to compute, how to check whether a given relation is reflexive, it's transitive, and also symmetric or antisymmetric. If the given relation R is not symmetric, you can also call that as asymmetric. Okay, but asymmetric is different, symmetric is different, and antisymmetric is also different. That's been explained in the regular class. It's called as a partial order or also poset. An ordered set poset. And poset is defined as a pair of element A, comma R within the ordered pair symbol. And this is called as a poset. Partial order. We'll understand that with an example. A familiar partial order relation called less than or equal to. Know that less than or equal to satisfy for the set reflexive property. We know that every element is to itself. Antisymmetric, yes, of course, it satisfies antisymmetric. When I do this equal to B less than A cannot possible. Okay, that's why it is anti. And is equal to C. Therefore, it is done. So you can write Z. Z is a set of all integers that is your given set Z with the symbol or relation less than or equal to is called as a poset. Similarly, a greater than or equal to will also satisfy similar condition. Therefore, this is called as a poset. You can just check with the divisibility relation, divisibility, Z plus A B. So how do you represent A divides B? So is a partial order on Z plus. That you can self. A divides B, yes, A divides itself for all the elements. Therefore, A divides B, but B cannot divide A, right? We know that. B does not divide. When A divides B, B does not divide A. Therefore, it is antisymmetric property. And transitive property is A divides B and B divides C. Definitely A divides C, which is a trivial result. Therefore, satisfies all the conditions. And it is a partial order. So we'll understand what is partial order on set. And it has to be called as total order on A. The condition is all the elements x, y in A, either this has to be there or y will y to y or y related to x. Any one must be there, not that is called total order. AR is totally ordered set. We see the example now. Partial order relation less than or equal to is on set R. The set R order on R. For all xy belongs to R relation, we have x less than y less than or equal to x. Or you can call this as a total. We take an example, for example, 1, 2, 4, 8. Okay. So the relation is not total order on the set 1, 2, 4, 6, 8. So that you have to understand here why this is a total order, but why not a total order? Because you have that relation defined here, divisibility relation. So 1 divides 2 divides 2, 3, 4 divides 4 divides 8 divides 8, true. For this, how do I check symmetric property? 1 divides true, right? But 2 divides 1 is not. So any one of the relation is present there. Yes, it is present there. Like this, you can check for all the. Similarly, you can also check with other two elements of a transitive property. But when it comes to this, 4, here every element should satisfy. No? 4 divides 6. No, 6 does not divide 4 also. Look at this. Neither this nor this. Therefore, at least any one of the element must be there. It's not at least exactly one must be there. Any one of must be there, but it's not satisfying in the second condition. Therefore, it is not a totally ordered set. Okay, like this, you can also check with other example. There are given a set S, S1, S2 are defined, and S1 is a subset of S2, S2 is a subset of S, but S1 is not a subset of S2, S2 is not subset of S1. Therefore, it's not a total order. So with that, we are moving on to Hasse diagram. Since a partial order is a relation on a set A, we can think of a diagram of partial order if the set is finite. So how do we write the Hasse diagram is, it's a directed graph of partial order. For the simplicity of the diagram, they have followed few things here for writing the diagram. So that diagram is also called as Poset diagram or Hasse diagram. Okay, and we know that for the partial order, reflexive property satisfies. That means self loop should be there in the diagram, but we don't write explicitly that self loop in the Hasse diagram. It is by default, if you are writing a Hasse diagram, it indicates that there is a self loop. Okay. In the similar way, if there is a transitive property, because we know that transitive property satisfies in partial order, and that transitive property will not be explicitly mentioned like this. If 1 to 2 there is a relation, 2 to 4 there is a relation, then there should be always 1 to 4 relation because of partial order. But this line will not be mentioned in the diagram. Only these two edges will be present, not this edge. It is understood by default for every Hasse diagram, the third element of the transitive property is present. Okay. In the similar way, there is one more condition here. For the simplicity, they have taken, since it is a directed graph, we don't mention the direction. We write in upward direction. Diagraph or Hasse diagram of this poset diagram is written in the upward direction. That indicates that direction is towards upward always. And all the edges points towards upward, and there is no arrow mentioned in that diagram. Okay, by default we have to assume that there is a upward direction arrow, and the vertices should be represented in bullets form. For the simplicity we have taken this. So with that, I will take a simple example to explain this and wind up the class, and rest two more topics to be covered. I hope you will read by yourself the last topic, that is extremal points on posets. Even that is there for the internals. Here there is no time to cover up that. Okay, so read by yourself. Take R as the relation. Verify R as a partial order on A. Also write down the Hasse diagram of R. So how do we do this is, we'll start with uh, partial order. First verify the partial order, and I will not verify the partial order whether it is partial order or not. You have to do by yourself because you know that partial orders should satisfy all three conditions. Okay, that three properties are satisfied with relation R or not. Check that. Yes, it is satisfying. Now I will just write how to write the Hasse diagram. Start with the first element 1. 1 to 1 there is a relation, but you no need to write all these self loops in the diagram as per the rules of the Hasse diagram. Don't write that. So just dot here, and the vertex name is 1. Next there is 1 to 2, there is a 1 to 2 relation. Yes, I will write that relation 1 to 2. Okay, next 2 to 4 there is a relation. I will write this also 2 to 4. Okay. Next 1 to 3. It's a different element. 1 to 3 I will write. Then 3 to 4 there is a relation. I will write this. But 1 to 4, 1 to 4 is an element which is of transitive property. Okay. But I don't write this edge. Okay, remember that you should not write this edge. You cannot write this edge in the Hasse diagram. By default, since it is a Hasse diagram, you will think that there is an edge from 1 to 4. Okay, this is called as a Hasse diagram for the given relation R. Any doubt here? Okay, so this is how you have to write all these details. Whatever I have explained, it is there here. So I'll just take another example and close this Hasse diagram part, and relations will be completed by this. Set A is defined as 1, 2, 3, 4. Relation xy is defined as x divides y, and prove that AR is a poset. Draw Hasse diagram. So you have to also check what is R here. R is not directly given. R is defined in this way, and you know that how to write this x divides y. In that format you have to write all the R elements. R elements is defined as ordered pair of element xy such that x and y must be there from the A, and x divides y. This condition should be satisfied. All such pairs will be written in the set R, and you know how to write this, right? So 1 divides all the elements. So 1 comma 1, 1 comma 2, 1 comma 3. Okay, so I will just clear all this and write the elements here. R is 1 comma 1, 1 comma 2, 1 also divides 3, 1 also divides 4. Okay, next 2 comma 2, 2 divides 4. 2 does not divide 3, so I am not writing 2, 3 comma pair. 2 divides 4. Next 3 comma 3, 3 divides 3 itself, and 3 does not divide 4. 4 divides 4 itself. So I will write only these are the elements. So with this you can check whether it is poset. You know how to check poset? Check first property, symmetric, antisymmetric, and transitive property. If all the three are satisfied, then it's a poset. So that you can verify later it's a poset actually. That's why we have to write Hasse diagram for this. So how do I write? So don't write this, don't write this, don't write this, don't write this. For rest of the elements, start from vertex 1. 1 is related to 2. Okay, I have taken this. Then 1 related to 3. Yes, I have taken this. 1 related to 4. But 1 related to 2 already taken. 2 related to 4 is there. 2 related to 4 is there. 1 related to 4 is your transitive property. Don't write that. Okay. So this is actual diagram. 1 to 2, 2 to 4, 1 to 3. Any doubt here? Okay. So this completes your relations and test portions. Since you are not replying to my questions or any kind of clarifications, I'll just wind up this. Look at this. There is another example here and extremal points.